After tone and all. Only 19 students are present. Is there any placement activity today? Is there any placement activity?
No, sir.
So why the strength is very poor? Very well less. Where you stopped yesterday? So harmonic indices are over, I think. Locating harmonics, these all the things over. Some VIP people are joining now. Bostamboli, Borate Aditya. Okay. The previous class we have discussed about harmonic indices and interharmonics. We have discussed already. So the harmonic indices, actually there are two harmonic indices are there. One is total harmonic distortion, another one is total demand distortion. This total harmonic distortion is for voltage, and this total demand distortion for the current we are going to consider that one here. Because this is voltage we are going to consider, this is current for harmonic currents we are going to use this indices, that is called TDD, TSD for the voltage indices we are going to consider. This is the RMS, it is the ratio of RMS value of the harmonic content to the RMS value of the fundamental quantity. This TDD, that is called total demand distortion, is the RMS value of harmonic current to the maximum or rated current we are going to call that one. It is the ratio of harmonic current, RMS value of the harmonic current to the rated current, that is called TDD, which is for the harmonic current we are going to use this indices. The TSD, total harmonic distortion, we are going to use for the voltage harmonics we are going to use that one. So it is 110. 110. I have waited for 10 minutes, then also some people they have not joined. So unnecessarily they are going to disturb. I'll lock the meeting better. Roll number 50 join हो गए better. वैष्णवी रघुनंदन. Okay. So the interharmonics we have discussed that it is not a integer multiples. It is not. But it is a harmonic only, but it is not going to multiply the integer value here now. So that is same like it is going to operate as a frequency, that is fundamental frequency only. So the next concept we are going to discuss. I will turn off the camera. So that is called resonance here. So everywhere in the harmonics, during the harmonics, the resonance will create the voltage or current to rise that one. The heavily it is going to rise that one here. So the resonance will occur. When the resonance will occur, what are the different types of resonance? What is the effect to the power system to that? Because of the resonance, we are going to discuss in this class here. Okay. So resonance means the general, the basic we are going to tell when inductive reactance is equal to the capacitive reactance, the resonance will occur. But actually, in the power system, we are going to use the loads or whatever some equipments, the load, inductive loads we are going to use, capacitive loads we are going to use. It is nothing but we are going to use some different inductances and capacitance we are going to use in that. Okay. So the motors and all the things we are going to excite, the DC motors we are going to use, suppose that one. Okay, excited DC motors are there. Okay, excitation system we are going to use that one. So because of using this inductances and capacitance, so some disturbances are already there. Excited, the disturbances are excited. On that condition, whatever the excessive voltage and currents are there, it is going to result. That means the excessive voltages or current will occurs over there. So that is going to call that one as, we are going to call as resonance, we are going to call, which is having a natural frequency, we are going to call the inductances, capacitance having natural frequency. See here, the condition for the resonance is a condition in which the natural frequencies of whatever the natural frequencies of inductances and capacitance in the power system, these natural frequencies are there, it is going to excite here now. It is going to the inductances and capacitance in the power systems are excited and sustained by a disturbing phenomena here now. So we have discussed in the previous, that is under voltage, over voltage. Okay, in that one, suppose voltage sag and swell, we have considered that. During that one, that is 5 cycles to the 30 cycles, 30 cycles to 2 seconds, 2 seconds to 1 minute. If it is more than one, that one we are going to call as sustainable fault or sustainable harmonic, sustainable the disturbance we have called that one. It is nothing but the manually we have to define that one and we have to solve that one. Like that, these systems are excited, the inductance and capacitance, sustained by disturbing phenomena here. They are sustained, that is more than 1 minute they are going to stay in the system. So because of this, the disturbing phenomena, sustained disturbing phenomena, the voltage and current value will exceed that one. It is going to increase that one. So that one, they are telling that one. So because of this inductances, frequencies of inductances and capacitance are excited and sustained by a disturbing phenomena. They are sustained by a disturbing phenomena. Because of this, or it can result in excessive voltages or currents, it is going to produce that one. The voltage or current, it is going to excess value, excessive voltages or currents, it is going to produce over there, or so value will be increases here. So this condition, that is called resonance, we are going to call that. The condition is resonance, we are going to call. Also because of this excessive voltage or current, if it is suddenly increase, decrease, increase, decrease, that one we are going to call as voltage waveform distortion only. Yes, so distorted waveform we are going to call. So waveform distortion, whether harmonic or non-harmonic, it is harmonic? No. Someone has messaged. Aditya Burate. Rule number 31.
Yes, sir. Yes, sir.
He came late, then you are suggesting that we admit him and all things. Huh? I was admitted.
नहीं सर, वो उनका मैसेज आया था, वो नेटवर्क प्रॉब्लम की वजह से लेफ्ट हो गए थे.
अभी मीटिंग तो लॉक की है मैंने, कोई भी इन नहीं हो सकते. एक बार मीटिंग से बाहर गए तो वापस नहीं आ सकते. आई हैव लॉक्ड द मीटिंग. बार बार हमने ग्रुप में मैसेज डालने के लिए नहीं होते. Just a minute. So due to internet connection problem, has disconnected. Just a minute. Is the screen is visible? Anyone of you? Screen visible आहे का?
No, sir.
Now? Now is it visible?
सर सर्च हो रहा है, लोड हो रहा है.
सर्च हो रहा है क्या? चेक करो एक बार.
हाँ विजिबल है.
Okay. So the natural frequencies of inductances and capacitance are excited. So and the sustained these frequencies are sustained by a disturbing phenomena. On that condition, it will result an excessive voltage and currents. So that will create a issue of the voltage increase or decrease. It is going to create that. Bolo Arvaj. Okay, so the waveform distortion, whatever the because of this excessive voltage and current is there, whatever this voltage waveform distortion will be there like this, it may be harmonic or it may be non-harmonic. We cannot say that one it is a harmonic only. So it may be harmonic content, it may be non-harmonic, or because of some transient suddenly the voltage fluctuation will occur over there. So that is condition we are going to call it. The waveform distortions is there, whatever the waveform distortion is there, it may be whether harmonic or non-harmonic. It may be whether harmonic or non-harmonic is probably the most frequent excitation source here now. So this is increasing like this, the pulses means that is most frequent excitation source we are going to call that now. The increase excessive voltages and current it is going to produce, that is called most frequent excitation source we are going to call it now. So sometimes what will happen, so because of harmonic only some resonance will occur over there, because of some we are going to use in the industries and all the things, the power factor correction purpose, we are going to use the capacitor banks and all the things. So that will also causes the harmonic distortion they can cause over there. Harmonic distortion they can cause, or without any harmonics also some resonance condition we are going to get here. How we are going to get? During the short circuit and open circuit also faults, on that condition also we can get the resonance, we can get that one. So also various short circuit and open circuit faults can result in resonant conditions here. This condition is that this condition may occur at short circuit faults and open circuit faults also. It can happen over there. So this is just concept of resonance. If the parallel circuit, the resonance circuit occurs, and that condition we are going to call as parallel resonance. If it is in the series, the RLC circuit, it is there. So that is, by considering that series circuit, we will call that one as a series resonance here now. So there are mainly two types of resonances are there. One is parallel resonance, another one is series resonance here now. So the parallel resonance we are going to consider now. What will happen in the parallel resistance? Okay, when the reactance will be capacitive reactance increases, then what will happen in the inductance or distribution system inductance? How they are going to cancel each other? So that one, based on that, the parallel resonance we have described here now. All circuits containing both capacitance and inductances have one or more natural frequencies. So our power system is there. Normally we are going to use our houses and all the things. We are doing a tapping over there. So parallel loads we can consider that one. In your house, the light एक room को एक parallel connection गया और एक room को another parallel connection we are going to call. The source is only one. So we are going to take the parallel branches. We are going to consider that. So like that, we are going to consider whatever the circuits we are using. All the circuits, whatever they contain, they are containing both capacitance and inductives. But these capacitive and inductances, any one of the load they may have, then more natural frequencies they can have. One or more than one also natural frequencies they are having. We are going to use inductive load, capacitive load. Everyone you are using in your houses, the fan you are using. This is actually capacitor we are going to use at the start of the fan before giving to supply to the winding. So capacitor start we are going to call that one. So that is, it may have the natural frequencies it may have over there. So that one only they are telling. All circuits containing both capacitance and inductances, you can consider any circuit or all circuits, they have contained capacitance and inductive loads they have contained. So, but out of this, all the circuits, any one circuit or it may be more than one circuits, they may have the natural frequencies. Yes, they may have the natural frequencies over there. So if the natural frequency is there, then what will happen? We will consider when one of these frequency lines up, that whatever the natural frequency is there, it is going to line up with the fundamental frequency or system frequency. That is going to called as parallel resonance. We are going to call actually. We are going to call as parallel resonance. Listen now. When one of these frequencies lines up with the frequency that is being produced on the power system here. So whatever in the power system, whatever the frequency is there, it is going to line up, both are line up. On that condition, the resonance may develop. So in the parallel circuit, this frequency lines up with the system frequency, that one natural frequency lines up with the system frequency, then the resonance will develop. That resonance we are going to call as parallel resonance we are going to call here. So they are telling this resonance may develop. What it is going to develop? The high voltage, high currents, that frequency, very high values it is going to consider that when it is going to produce over. Okay. So this system, when those frequencies lines up with the frequency that is being produced on the power system, a resonance may develop in which voltage and current at frequency continue to persist at very high values here. Whatever this voltage and current at that frequency, both when lines up over there, on that condition, they are going to continue persist at very high values. They are going to persist over there. Suddenly, suppose single phase I will consider 230 volt is there. Okay. When the natural frequency is going to tie up on that condition, so it can vary suddenly high value of voltages. The for particular frequency means same, we are going to use that one here. This voltage or current, it is going to high over there. It will come back like this. So persist, very high values it is going to persist over there. This is the root of most problems with harmonic distortion on power system. Here the distortion it is there, waveform distortion is there. So this root, this is the root of most problem here. Now this is root for most of the problem. This is the starting they are going to found over there here. From the perspective of harmonic sources, the whatever the non-linear load we are going to use, from that the harmonic sources, the shunt capacitors appears in the parallel with the equivalent system here. Whatever one side we are going to, the system inductance is there. So in that, the parallel with that, the shunt capacitor appears here. So the inductance and the capacitance both are connected here, parallel here. Parallel, they are going to connected here. This one we are going to call as system inductance we are going to call. This one we are going to consider as the shunt capacitor we are going to consider here. So the harmonic, the shunt capacitor appears in parallel with the equivalent system inductance, source and transformer inductances we are going to consider at harmonic frequencies here. At harmonics are already there. At harmonic frequency, they are connected in parallel here. Now, since the power system is assumed to have an equivalent voltage source of fundamental frequency, our requirement is that this system, we should have to get the equivalent voltage of fundamental frequency only. Fundamental frequency is 50 Hertz only. Fundamental frequency is 50 Hertz only. But here the inductance are there, here capacitance are there. They have one or more natural frequencies they are having here now. Yes. So when the parallel resonance occur, when these two will become equal, so parallel resonance will occur. On that condition, the reactance of XC, whatever this XC value is there, and disturbance distribution system cancel each other. This distribution system, actually here, impedance of the distribution system we have to write, not impedance, that inductance of the distribution system. So the inductance of distribution system, that is XL and XC, both will get cancelled here now. So that condition, we can say that the parallel resonance occurs over there. So the frequency at which this phenomena, when the XC equal to XL or XC cancel the XL, on that condition, that frequency we are going to call as parallel resonant frequency we are going to call that. The condition is very simple. We are going to use the capacitors and capacitance. We are going to use that one here now. So which is connected in parallel with the system inductance here now. So during the resonance, what will happen? This XC will cancels with the system inductance here now. So that one we are going to call as parallel resonance. During this phenomena, at this phenomena, whatever the frequency is there, that frequency we are going to call as parallel resonant frequency we are going to call here. That is called parallel resonant frequency. Any doubts here? Any doubts? Okay. So next we will go for the series resonance. We'll discuss about that one. So here we have connected one shunt capacitor here now with system inductance. So that condition we have considered as parallel resonance over there. But in the series, what we are going to consider, the resistance and inductance and capacitance both will, whatever the shunt, instead of shunt capacitance, the capacitance we have connected in series LC circuit we are going to consider. The resistance is commonly we are going to use. So that is LC circuit we have used here now. This is the inductance, this is the capacitance of the circuit we have used here. There are certain instances when shunt capacitance and inductance of transformer or distribution line may appear as this shunt capacitor and inductance of the transformer or distribution system or line that may appear as series LC circuit to a source of harmonic currents here. For the source of harmonic current, it may appear as series LC circuit. That is, L and C both are connected in series here. If the resonant frequency, whatever during that condition when XL equal to XC, on that condition, if the resonant frequency corresponds to characteristic harmonic frequency here. Now here, the harmonic frequency of the non-linear load, we have to consider that we are going to use the non-linear load frequency also we are considering here now. So that is corresponds to the resonant frequency corresponding to the non-linear load frequency. Then the LC circuit, this series LC circuit, what it is going to do, it is going to attract a large portion of harmonics here. Can use as a filters also. It is going to attract whatever the large portion of harmonic is there, harmonic current, it is going to attract, and that is generated in distribution system here now. Where we are going to connect this LC circuit in the distribution system, we are going to connect. So when the resonant frequency, it is going to correspond with the non-linear, harmonic frequency or non-linear load frequency. On that condition, what they are going to do? This LC circuit, it is going to attract the large portion of the harmonics. It is going to attract here now. So it is connected in the distribution system. That will, this current will be generated in the distribution system. Suddenly it is going to give the spike, or it is going to increase the large change in the voltage. A customer, suppose a customer having no non-linear load, he don't have any non-linear load, but utilizing the power factor correction, he is going to utilize the power factor correction. Power factor correction ke liye what we are going to use? Capacitors here. So he is utilizing the power factor correction capacitors, he is utilizing over there. Okay, so up to here, this is basic. Here we have taken one example here. May in this way experience high harmonic voltage distortion due to neighboring harmonic sources here now. Here we are not considering the same circuit here now. In the neighboring circuit also any harmonics are there. So I have not used any non-linear loads, but the neighboring system, it has some non-linear loads, but I may use the capacitors for the power factor corrections here now. Because of this capacitor, what will happen? The neighboring circuit harmonics produced over there, that it is going to attract that one here now. It is going to attract here now. So where it went? Attract the harmonics here now. It will carry here now. So if you are having the non-linear load or not, but anywhere in the system, if the harmonics are there, the harmonic frequencies are there, then that harmonic frequency, if it is correspondent by a resonant frequency, then though anywhere if you have used the capacitor banks or inductance circuits, LC circuits, it is going to attract the large portion of the harmonic current. It is going to attract, and that situation, it is going to give the very high value. It is going to give here. So it is going to experience a high harmonic voltage distortion. It is going to experience because or due to the neighboring harmonic systems, it may be occurs. During the resonance, what will happen? During the resonance, the power factor correction capacitor forms a series circuit here. Now, during the resonance, it is going to form a series circuit with the transformer and harmonic sources here. With a transformer and harmonic sources, the whatever the power factor capacitor is there, during resonance, it is going to forms that a series circuit here. So the inductance in series with the capacitor is that service of entrance transformer. It is the entry of the transformer we are going to consider here now. So this series combination of the transformer inductance and capacitor bank is very small. Theoretically, we are going to use 0 and only limited by its resistance here. So we are going to use the resistance, inductance, capacitance means the resistance you should not consider as 0. It has some, the conductor also, it has some resistance. So we can consider only it is limited by the resistance only we are going to consider here. So the harmonic current corresponding to the resonant frequency will flow freely in this circuit because the value of this inductance and capacitance is very small. Theoretically, we are going to consider as 0. So this is limited by a resistance. The current is limited by a resistance here. Now, on that condition, what will happen? The harmonic current, it is going to correspond to the resonant frequency and it will flow freely in this circuit. It is going to flow over there. Any circuit, it is going to flow in this one here. So the voltage at power factor correction capacitor is magnified and highly distorted here. Now it is magnified to the one value and it is highly distorted voltage we are going to call that. So this is the series resonance we are going to call that. Series resonance, this is parallel resonance, and this is what you mean by what is the condition for the resonance we have discussed here. If you have any doubts, you can ask me. Okay. So next we'll go for that harmonic distortion evaluation we are going to call that. Okay, harmonic distortion evaluation. So actually the harmonic evaluation, distortion evaluation we can do by using three principles we are going to use. Three places we can call that. One is the end users, another one is utility, and third one is that is common coupling point we are going to call that one. That is PCC we are going to call that. Common coupling point. So in these 3 points only we can evaluate the harmonic distortion here. Harmonic distortion we can use. One is end side. Utility means whatever the substation through we are going to get here now. So here the generation is there. So you can consider that one here from to whom you are going to pay the electricity bill. Anyone, can you tell me? MSDCL, na? What is that? Here the generation is there. Here next we are going to step up that one, generating substation. Next we are going to transmit and primary transducer, secondary transducer, next primary distribution, secondary distribution, and we are going to get the utility here. This is the end user here. I will draw the diagram neatly over there. Here we are using the generation here. The L1 kV generation is there. So in the generating substation we have cleared here now, that is called GS side, consider that one. Next it will go for the primary transmission system, PTS. Next one will go for the secondary transmission system. Next we'll go for the primary distribution system. Next we'll go for secondary distribution system. Secondary distribution system, and the last one is that is called, we have considered that is called the customers or end user we are going to call that. End user we are going to call. It can your house wiring or whatever the load you are using in the end side, that is called end user we are going to call that. Okay, so from this one primary distribution system we can give many secondary distribution, we can give that one. Can give many secondary distribution systems, we can create that one here. Now it may be one area from the primary distribution system from L1 kV, we can give so many points, we can convert that one, divert, we can give that one. So here this part is end user, this part is utility side we are going to call that one. Whatever this point is there where it is more utilities and the end users are connected, that is called common coupling point we are going to call that. That is called common coupling point here. So under these three places only we can evaluate the harmonic distortion here now. Okay, one is that is end user, another one is that is utility side, okay. So there are three places are there, whatever the harmonics are there, we can identify. One is the utility side, another one is that is end user side, and the in between where the end users and utilities connected, that is two or more utilities or end users are connected, that point we are going to call as common coupling point, we are going to call that. So that places we can connect the, that is we can evaluate the harmonics here. Now, these harmonic evaluations are there some by IEEE standards. We are going to define that one here. We are going to observe that one. We are going to evaluate that one. Here for individual end users, for here that is we are the individual end users here. IEEE standard that is called 519 and 1992 limits the level of harmonic current injection. Whatever it is going to limit the, whatever the level of harmonic injection is there, that current harmonic current injection at the point of common coupling point. I will consider here, see here. Okay, this one is common coupling point. We are the end user here now. End users are connected at this point. PCC it is connected here now. Okay, at this point, whatever it is going to limit the harmonic currents here now. Whatever the injection of harmonic currents, it is going to limit that one according to IEEE standard here. At the common coupling point, this is the quantity end users have control over that one. Because of this one, so the harmonic quantity, the end users have the control on that. Yeah. Next one, recommended limits are provided for both individual harmonic components and the total demand distortion. Just a minute. we'll stop here only and we'll continue in the next class.